We're going to proceed now to hear from Hank in Missouri, and you can go ahead and introduce yourself, Hank, and share your screen and show us your stuff.
All right. Am I sharing successfully here?
Yes, you are, but speak up a little bit, please.
Okay, how's that better?
Okay.
Good afternoon, everyone. It's nice to be able to share the research that I'm doing here with my students. As an overview, most of you are probably well aware of the so-called small sat revolution that's going on in the last 20 years or so. And that's also led to an expansion of university design build flight paradigms. And actually, the small sat revolution really began at the universities, too, in California. I came to Missouri S&T in 2001 and quickly started our satellite research team here, where we are working on a number of small satellite and CubeSat projects. We've been focusing on our campus's expertise with GNC and small sat propulsion. And so, as I mentioned, we have 3 technology demonstration missions that we have ongoing right now that I'll talk about toward the end of my talk today. But while we have been developing our satellite team here, I've really been using that as a sort of a backbone, a complement to my higher level research that I do with my graduate students, and extending that to formation flight, and most recently swarms, which is what I'll be focusing on today. So small sat swarms have recently gotten a lot of good attention from especially NASA, but also DoD and commercial entities. And my research with my students has focused on scientific applications so far, a little bit of low Earth orbit, but mostly scientific in the deep space regime, specifically at the libration points where my core area of expertise is. And so in the space environment, there's a number of areas we'll talk about how to swarm, and that's where my title comes from, and trying to herd cats. So to begin with, swarms might have up to 10 or even 100 small sats as envisioned by NASA currently. And so that's a lot of spacecraft to manage. And to start with, then determining the best geometry, best orbits, relative orbits, the best guidance solutions is a non-trivial aspect. And so I have a PhD student focusing on that right now. Once you get on that, then of course navigation is important. So out in deep space, GPS is not available. And so trying to figure out where the swarm is and everybody within the swarm is relative to each other is a big challenge. I have another grad student working on that. And then finally, controlling each member of the swarm is challenging, as micropropulsion systems, especially for small sats, is still not really technologically advanced quite yet. Other challenges sort of outside my area of expertise include communications. So the DSN availability is limited to deep space entities, and especially if you have 100 spacecraft in your swarm, you're not going to be able to talk to all 100 of them through the DSN. And of course, there's latency as well. It'll take the signal to get around these spacecraft. And again, with so many spacecraft, autonomous operations are probably desirable, if not required. Initializing the swarm from launch vehicle out to its final destination is challenging. And then once you get into that swarm, maybe you need to reconfigure it for another mission purpose. So that's also a key challenge. And finally, you want to try to do all these things within the package size, of a 6U, 12U CubeSats. That brings up the swap challenges of size, weight, and power. That's difficult to do in a CubeSat or even a small sat format. But there are some key benefits, and as most of you are probably well aware by now, small CubeSats compared to the larger monolithic spacecraft are much cheaper. Typically, it's faster to assemble, integrate, and test these, easier to launch on average. And then finally, if a unit does fail, it's not always the end of the world. They can be easier to replace. Or in the swarm, you might just have a few spares there from the get-go, ready to step in should one of the main members fail. So as I mentioned, what we've been focusing on is the libration point neighborhood. So to give a little background there, many of you probably are not that familiar with libration points or their dynamics. So my diagram here with the mouse, I'm circling what's called the first primary, the larger primary. So in my research, that would be the Earth. And then out here, the moon, the second primary, of course, orbiting the Earth. And if we look at a line between the Earth and the moon, that line then rotates with the moon, and within the rotating frame, Lagrange back in the 1700s found 5 locations called libration points where we can position objects and they'll stay there in a dynamic equilibrium. And so my diagram here shows 2 of those points, the L1 point here between the Earth and the moon, and then the L2 point out here beyond the far side of the moon. So the L2 and L1 points are about 60,000 kilometers away from the moon, give or take. And so the spacecraft here then flies this area where there are now 2 gravitational sources affecting its orbit, as opposed to the more common single gravitational force. So Keplerian orbits really don't happen anymore. We have relatively complicated orbits, and we can find orbits about these libration points, which is where my work is focusing on. So this next slide here shows one example of that in an application. Of course, we, NASA and others are focusing on going back to the moon with humans in the near future. Communicating with humans and other assets in the lunar region is, of course, very important. So back in the 1960s, when the latter Apollo missions were looking at putting astronauts on the far side, a NASA engineer suggested a spacecraft in this orbit back here on the far side of the moon. And from Earth, he thought it looked like a halo, so he called this a halo orbit. And the advantage of this orbit is a spacecraft can simultaneously see the far side of the moon here, also see all of the Earth and communicate back to the Earth. And so that was his proposal back then. And so our idea now is to add to that by also putting a spacecraft at one point. And if we put them out of phase with each other, each spacecraft will view about a hemisphere of the moon and provide near continuous coverage to the lunar surface and objects orbiting around the moon. So in support of that, NASA has been developing something called LunaNet, a series of spacecraft orbiting the moon that provide a internet-like communications as we have on Earth at the lunar vicinity, provide communications with any kind of lunar assets. But in the early trade studies, they didn't find that halo orbits were really useful. And so my research is revisiting that with the possibility of using sats, swarms, laser communications as that technology also matures. And so that's what we've been studying here lately. And so to do that, and we've got to tackle the big 3 with those challenges I mentioned earlier, which are guidance, navigation, and control. So as I mentioned, I have a grad student working on this, and this slide summarizes what she's been working on. These orbits are all unstable. So in this diagram here, this shows 3 different views of one of these orbits. So the dot here in the center in this upper right-hand figure, the upper right-hand figure is a 3-dimensional view of one of these orbits. So this black dot here would be sort of a leader spacecraft of the swarm on one of those halo orbits that I have on the previous slide. And then we have members of the swarm buzzing around in the orbit that's shown here. So you can have any number of smaller spacecraft in this swarm orbit here. The range here between these 2 spacecraft could be anywhere from 10 meters to 100 meters, even up to a kilometer, depending on what you want the design to do. And these other 3 views here just show 3 different projections of that same orbit from different viewpoints. There's really not enough time to go into a lot of detail with the geometry here, but suffice it to say that it's pretty clear that these are not your typical elliptical Keplerian orbits. These are 3-dimensional, a little bit complicated orbits. And so it's important to calculate these paths accurately, and because they're unstable, we need good fidelity in the models that we use for these. The good news is they're relatively easily maintained in spite of that instability, but accuracy, fidelity is required, and so we're working on calculating those orbits with that needed accuracy. Once we're in the swarm, then we have to be able to navigate, and so the swarm must know its inertial position and attitude. It also needs to know where its swarm mates are, and again, without using GPS. So I have another grad student working on using visual navigation techniques with a single camera on a spacecraft, imaging the other spacecraft. These other spacecraft might have some kind of beacons on them, LEDs, QR codes, some identifying marks. And so we're asking the question, can deep space artificial intelligence solve this problem? And so we're just now getting into this, the beginnings of this research, and we're looking at using unsupervised forms of neural nets to do this, expanding on terrestrial methods that have been developed now for self-driving cars and other similar kinds of applications. And we're finding that using unsupervised as opposed to supervised networks, we can track multiple objects over longer periods of time instead of focusing on a single object over a shorter period of time. And longer term, we've been scratching our heads that this might have applications in other areas such as collision avoidance within the swarm, and perhaps even astronaut EVA navigation. And finally then, with guidance and navigation underhand, we need to control these things. It's a good news, bad news kind of thing. The good news is that the control inputs are very small that we need in order to affect this control successfully. The bad news is that the control inputs are very small. And they're so small that we really don't have propulsion systems that can execute the control inputs, the maneuvers, at such small levels where the resolution is accurate and we can accurately provide what the controller is asking for. So our control design gets complicated by that, and we have to be careful that we can accommodate the limits on the thrusters as the current state of the art allows. So the two graphs there below just show a sample run that we've done, showing as a function of time here in hours, tracking the position error in the top graph, velocity error in the bottom graph. And we were looking at two different guided solutions, one a linear approximation, and then a numerical one. And we can see that the numerical guided one is easier to maintain. Again, showing the importance of having good guidance solutions. So this is just an animation here, or actually a simulation of one of those swarm orbits that I had on that previous slide. Again, you can see the very non-planar nature of this. One of these orbits in the Earth-Moon system takes about 2 weeks per orbit. So the spacecraft move relatively slowly, which is a nice attribute for astronauts or assets on the far side of the moon. Your antenna pointing requirements become simplified because of the relatively slow motion compared to the faster motion that you would have in a orbiting lunar type of network spacecraft. One other application that I'll run through quickly here, because I'm running short on time, that we're looking at is within the swarm concept. Another related concept that's been talked about the last 10 years or so is the fractionated concept, where your swarm is divided, where each member of the swarm has a single focus job for the swarm. So in this block diagram here, each of these blocks is a single spacecraft and has its own function. So for example, the upper left here is our GNC spacecraft. The only thing that it does is determine its inertial attitude and location. And then it passes that information on to the central small sat, CubeSat swarm member here, the CNDH spacecraft. It's kind of the brains of the swarm. So it has flight software memory, and it learns, understands where everybody is, and then informs everybody else of what's going on. So moving back up here to the top right, and we would have that visual navigation spacecraft that I mentioned a couple slides back, where we have cameras, or maybe many cameras on that spacecraft, and it visually navigates and figures out where everybody is, tells the central spacecraft, and then the central spacecraft tells everybody else. And then over here on the right, we would have a number of payload spacecraft. Could be telescopes, small telescopes, or a communication payload, whatever it might be. and that payload does its job. It gives its information to another spacecraft, which is a high-gain antenna communication spacecraft, who sends the data back to Earth or wherever it might be needed. Each spacecraft would have some kind of attitude control, reaction wheel, and some kind of thruster or orbit control. And that would all be controlled, again, by the CNDH spacecraft, which would command each of those thrusters and reaction wheels, how to maintain each of the spacecraft in the swarm. So it's kind of an out there concept, but it's something that we're looking at as another possible application. And finally, I'll run through this slide quickly. I mentioned early on that we have our satellite team here working on flight projects. So that's been established, again, to complement my higher level research that I've just summarized. And our key goal here is to build small sats that are flight ready, teaching spacecraft design, integration, test, operation, but also developing small sat technologies that can extend the state of the art. And we've also been pretty active in K through 12. Like Matthew, we have a high altitude balloon program here and a couple other outreach projects we have going on. Very quickly, our active projects are a pair of microsats, MrSat and MissaSat, that will launch together. That's shown in the picture on the lower right there. They'll separate on orbit, and then MrSat will use his stereo vision cameras to navigate around MissaSat using a cold gas propulsion system. And then we have two related CubeSat missions, Apex and MCube, both testing a multi-mode thruster system. It's a thruster that can operate both in high thrust mode and low thrust mode. The high thrust mode is a little less efficient than the low thrust mode. So this kind of thruster would be ideal for the swarm concept, where when you're just maintaining the swarm, you use your low thrust efficient thruster just to tweak things a little bit. But if you need to reconfigure, do some big orbit changes, you use the higher thrust mode to do those kinds of things. Our team has freshmen through PhD students, so we involve underclassmen as well as my students doing the higher level research. We have all majors from across campus here, and a few different faculty and staff also helping out, as well as industry and government partners. We're tied in heavily with the Air Force as well as NASA, and then a few industry people. And so with that, I'll move on to questions. You can see one of our students here on the right, hard at work in a lab, and then one of our other team members, key team members, showing off one of our polos that we make all our team members wear. So with that, I'm open to any questions any of you might have.
So thanks a lot, Hank. Maybe time for just one question. Anybody?
I got one.
Demos has got one.
I got here late, so I probably missed the earlier parts of it. So on the GNC, the algorithms for GNC, are they, it was not quite clear if it's all, is it going to be centralized or is it decentralized or is it?
Go ahead. Yeah, so it's a work in progress. There's a good bit of material in the literature on the pros and cons of centralized versus decentralized. We will be focusing on largely autonomous control. And again, it depends whether we're looking at the fractionated concept or exactly how the swarm will be operated. We're also tinkering in the LunaNet concept of going to a constellation as well, either in addition to the swarm or instead of the swarm. So we haven't really gotten down into the weeds yet of exactly how we'll be doing that control. So we're in the literature survey part. We've done a few basic simulations, but we haven't really figured out what our first go-to method will be.
Right. Okay, thanks again, Hank. So your contact information is on the flyers, and we'll post this stuff and people can get in touch with you if they have more questions. So thanks.
Great.
Let's go on. If you would stop sharing your screen, Hank. Thank you. To